Still talking a little bit about timescales, but we're going to go from the Big Bang timescale now to the geological timescale. And we've got Hilary joining us, who's going to talk about the rock cycle. Hilary has also got some slides that I'm going to be sharing from this end. So just bear with me while we share those. Hello, Hilary.
Hello.
How are you this afternoon?
I'm very well, thank you.
Jolly good. Okay, so I'm just queuing up your slides. So as you talk, I can move them through. So thank you ever so much, Hilary, for joining us and talking a bit more about geology, particularly as we had Mark on earlier talking about fossils.
This is true. Right, I'm going to talk about the rock cycle, which is a process that takes place near the surface and just below the surface of the Earth. And it's an ongoing process which happens over intervals of time, but over a very long period of time. Next slide, please. So we're going to start with the structure of the Earth. As you can see, this is not what the surface of the Earth looks like. This is as though we've taken a large knife and cut straight through from the North Pole to the South Pole. And we can see on the outer layer, there's the crust, which is divided into two layers itself. There's the continental crust, obviously, which is the land surface. And then there's the oceanic crust, which is the layer of rock that forms on the ocean floor. Underneath that is the mantle. Now, this is the largest mass of the Earth. It's composed of, we used to think it was liquid rock. It is very hot rock, but it's more like a very thick syrup with mushy crystals in it. And this is what actually creates rock on the surface, well, one type of rock on the surface. And in the middle of the Earth, we have the core, and the outer core, which is liquid, and inner core, which is extremely hot. And both cores are made of iron and nickel. Right, well, we're going to look at rocks, and so we need to decide what rocks are actually made from, and they're actually made from minerals. Sometimes one mineral, but more often they're a mixture. I tend to think of them a bit like a cake, making a cake, and you have all the ingredients, and if you change one of the ingredients, you end up with a slightly different cake. Sometimes good, sometimes not so good. On the left-hand side of the screen, you can see three very common minerals, and they are mica, feldspar, and quartz. And these are fairly good crystal forms of these three minerals, and I will explain a few slides further on exactly which rock they come from. On the right-hand side of the screen, there are four minerals: copper, calcite, iron, and fluorite, and they're just four of the 4,000 plus known minerals on Earth. The minerals make up rocks, and we have three major rock types. There's igneous. When material moves up from the mantle and begins to solidify from that material, we have igneous rocks. So they're solidified magma from the mantle. Next, we have sedimentary. If you can imagine that all rocks at some point will get broken down and then the remains become joined together. These are the sedimentary rocks. And then metamorphic rocks, which have been changed by heat, that's cooking, or pressure, that's squashing, squeezing, or both. Right, we'll have a look at the igneous rocks. They were the very first rocks to form on Earth from the cooling Earth. And they're formed by, now we've got a star here, and it says crystallization afterwards. If there's a green star, it means it's part of a process within the actual rock cycle. Further on, we'll see red stars, and that means it's actually a rock type, like sedimentary, igneous, or metamorphic, or it is actually a rock, a named rock. So we've got crystallization of cooling magma from the mantle, and it can either form two sorts of igneous rocks: plutonic rocks or plutons, which are intrusive into the rocks above the mantle, so into the crust, or it can form volcanoes, which means that that magma has come out on the surface of the Earth. Right, so what sort of intrusive igneous rocks have we got? Well, they're crystallized deep in the Earth's crust, and these plutons cool very slowly. So they've come up from the magma, they've sort of run out of steam, they can't get up to the surface. And so it's this slow cooling down, and very large crystals develop as a result of that. So on the left-hand side of the screen, we have got a granite, which you'd find or see if you went through Dartmoor or down into Cornwall, Bodmin Moor, or up to the Lake District at Shap. This particular one is a Dartmoor granite. And if you look closely, those three minerals that I showed you earlier on, the biotite, which is the black, the biotite mica, the feldspar, which is the milky white, large crystals in this particular rock, and the quartz, which is sort of glassy grey colour. They form the three major minerals which form the granite, and granite is normally found in the continental crust. Whereas on the right-hand side, we've got a gabbro. This particular one is from the Black Coolin Hills on the Isle of Skye. As you can see, it's got large crystals in it, but they are a very different origin. It's got feldspar, but it's also got those very dark minerals as well. So igneous rocks that have been intruded as plutons have the larger crystals. However, if that magma works its way a little higher into the crust, but still doesn't get quite to the surface, the surrounding rocks means that they're cooler itself, and it cools this intruding rock much faster. Faster cooling means the growth of much smaller crystals. So it crystallizes with these little crystals, but you can still see them if you look at the rock that's on the screen. This is a dolerite from the Great Wind Dolerite Complex in Northumberland. I always used to know it as the Wind Sill, and I always think of it as being the feature that Robin Hood was standing on during, well, Kevin Costner playing Robin Hood, but it's actually on Hadrian's Wall, sorry, excuse me, forms the top of the Wind Sill. So here we've got a dolerite with sort of smaller crystals, but they're not tiny. However, if the magma makes its way up to the surface of the Earth and erupts at the surface, we then call it a lava. And because it has contact with the air or the water, it cools very, very quickly. And so very small crystals form. And the lava itself forms volcanoes. To actually see the crystals in this type of lava, you would need a hand lens because they are extremely small. Now the lava, depending on where it actually comes up to the surface, can form two different types of volcano. The one on your picture, that's sort of a long base triangle with very low angle sides, is called a shield volcano because it's supposed to look like a Viking shield laid down on the ground. And the lava which forms these particular volcanoes is extremely runny and flows very, very easily. And if you've seen photographs, for example, of lava flowing on Hawaii, you'll know it runs quickly and it is very runny, and usually cools off when it reaches the sea or just sort of tails off and then goes hard. An example of this particular rock is basalt. And although they normally come up at the mid-ocean ridges or hotspots, places to see these basalts are Iceland, and which is along the mid-ocean ridge, the Atlantic, or Hawaii, which sits astride a hotspot. However, some volcanoes don't erupt basalt lavas. the quartz content or the silicon dioxide content of these particular lavas is much higher, and that makes them very much more sticky. They don't flow easily. And so when a volcano has erupted or is erupting, those particular lavas can actually be so sticky they won't even flow out of the volcano, and they form a cap and block the vent. And underneath this, you can imagine if an eruption is sort of imminent and you've had gases going off and things, the gas gets trapped and builds up, and that can cause catastrophic eruptions, which are very, very sudden, a bit like explosions. And a good example of this is the rock andesite. And as you can see it in the picture, you can still see crystals, so it's sort of medium grained rock. And the type area, obviously, for these cone-shaped, typical shaped volcanoes that we imagine a volcano to look like, would be the whole of the Andean chain in South America. And of course, Mount St. Helens in North America, which erupted, I think it was 1983. And there is very good coverage if you want to go on the internet and have a look at a big eruption taking place. Okay, so we have these rocks on the surface of the Earth. Once they're there, they just don't stay there as pristine pieces of rock. As soon as they emerge, then the atmosphere and the weather starts to react upon them. And this we call weathering. And so the rock in situ, it can be dissolved by rainwater, or it can be broken down by the action of water going into small cracks in the rock, excuse me, and ice forming in those cracks, and then breaking it apart as the ice expands into tiny pieces. So that's weathering in situ, where the rock actually is. Now then, it doesn't stay there. Erosion happens to that material, and so it's picked up by various agents. It could be ice, if it's a glacier, it could be water, or it could be wind blowing those pieces of rock or moving them downhill, transporting them to another place. So we've got this material being transported. So then what happens to it? It's taken downhill, obviously. Very few things can actually move uphill on their own. And it's deposited, sometimes in lakes, sometimes in a delta at the coast or at the sea. And here it builds up in layers called sediments. And I would suggest here, if you want to try this at home, you get yourself a pop bottle that you can see into, cut the top off, take a good handful of your soil from your garden, mix it with some water, and then just have a look over a week or so to see what happens in your plastic container, and see if you can see any layers building up. And what you should find is that the more coarse material sinks to the bottom, and you may see sand in amongst your sediments, but your finest materials will take a very long time to settle right at the top, we hope. Anyway, these sediments are formed into sedimentary rock because they more and more gather on top of them, and it's the weight of those that actually compress them, and they become compacted and then joined together. And this process is called lithification. So we've got quite a few processes going on here. It had deposition, we've got burial, compaction, and lithification. And here's some examples of some sedimentary rocks. There's a limestone, which is formed in the sea from calcium carbonate. Then there's a sandstone, which is grains, small tiny grains of quartz usually. And if you rub a sandstone, it is literally like rubbing sandpaper. Then there's chalk, which is formed by the shells of tiny, tiny creatures called coccoliths. Well, that's the shells of coccoliths, and settling on the bottom of the sea. And then there is coal, which is formed from plant material, which is being compressed, and it's a carbon-rich rock. And you heard this morning from Mark O'Dell about fossils, and this afternoon, I believe, as well. And I'm sure you've seen some absolutely wonderful fossils. Sedimentary rocks contain fossils, plant or animals trapped in the sediments as the rock actually formed. And here I've got, well, I think it's a lovely, friendly little model of an ammonite. And there is a piece of ammonite underneath. And on the right-hand side is a sea urchin from around 65 million years ago. And as you can see, it's got the 5 arms of symmetry. We call that pentasymmetry along the top there. And the last group of rocks we've been looking at, well, we've been looking at igneous, we've looked at sedimentary, and the last group is metamorphic. And these rocks were once igneous, once sedimentary, or once metamorphic. And they're being changed, that's metamorphosed, as a result of this intense cooking or pressure and squashing deep within the crust. So this normally takes place right deep below the sort of huge continental land masses. It's a long way down. And there are huge pressures and it's very hot down there. So these metamorphic rocks will only be seen then if they've been uplifted by other pressures and exposed on the surface. Otherwise, we wouldn't know they existed. They don't come up. They're not just there on their own. So types of metamorphic rocks, well, we've got clay, which is sedimentary, changed to slate. Sandstone, which is changed to a quartzite. Limestones get changed to marble, and granites get changed to a rock called gneiss. And here we've got some examples. There's slate on the left-hand side with, it is slate, it's not slat-e, sorry. And it's got very, very fine layers within that slate. Obviously it's used for roofing tiles because it is extremely waterproof. Then on the right-hand side at the top is the metamorphosed sandstone, yes, which is a quartzite. And then down at the bottom is the gneiss, which is a metamorphosed granite. And as you can see, although it's got lines going across this particular specimen, it can see that it's still got the original minerals from that granite. You can see the dark biotites, you can see the feldspars, and you can see the glassy quartz. Right, so this is a diagram of the actual rock cycle that we've been looking at. And if you follow it up from crystallization of magma on the left-hand side, this is the process that I've been talking about so far. So magma rises and you get crystallization either in the crust as plutons or up above the crust as volcanoes and lava spewing out. These rocks then appear on the surface after a very long time in terms of plutons, but they're obviously there straight away in terms of volcanic rocks, and they become weathered at the surface. That weathering then is acted upon by erosion and transportation, and the little particles are taken down and deposited as sediments. After burial and compaction, those particular sediments become sedimentary rock, which is the lithification process. Then they sink down under weight and pressure and become deformed and metamorphosed. And then those rocks can either be uplifted, as you see in the center there, or they can become molten again and magma and rise up, and the whole rock cycle begins again. And here are some rocky facts. It can take millions of years to build a mountain and hundreds of millions of years to wear it away. So this particular cycle is not a very fast acting cycle. The oldest rocks on Earth have got a very strange name. They're called a faux amphibolite. And as you can see, they are exceedingly old. This is in Hudson Bay, Quebec, Canada. And what they are is a metamorphosed gabbro type material. And then the oldest mineral on Earth is a zircon, which comes from the Jack Hills in Australia. And a rather beautiful mineral as well, if I may add. Right, well, we're nearly finished. I just wanted to know whether or not, pose a question, if Stone Age man knew about the rock cycle already. Perhaps he did, those nice rocky wheels. And I've added this in case you want to know some more. Here are some, well, 3 local things that you could find more to interest you. And then there's the Rock Watch, which is the nationwide club for the young geologists at the bottom there. So geology is a fascinating subject, and I'm pretty certain that you've heard from physicists, chemists, biologists, mathematicians, all sorts today. And there are branches of geology which actually can be entered from any of those subject backgrounds. That's it. Thank you.
Thank you very much, Hilary. That's great. And indeed, geology is related to a lot of the other subjects we've been hearing about today, and people studying chemistry and physics and so on at school could go on and be geologists later, of course. So if they have any questions, they can ask you them in the panel. Thank you very much, Hilary, for joining us. That was a fascinating talk explaining the rock cycle.